Fertilizer is any organic or inorganic material of natural or synthetic origin that is added to soil to supply one or more plant nutrients essential to the growth of plants. Conservative estimates report 30 to 50% of crop yields are attributed to natural or synthetic commercial fertilizer. Global market value is likely to rise to more than $185 billion until 2019. The European fertilizer market will grow to earn revenues of approximately $15.3 billion in 2018. Mined inorganic fertilizers have been used for many centuries, whereas chemically synthesized inorganic fertilizers were only widely developed during the Industrial Revolution. Increased understanding and use of fertilizers were important parts of the pre-industrial British agricultural revolution and the Industrial Green Revolution of the 20th century. Inorganic fertilizer use has also significantly supported global population growth. It has been estimated that almost half the people on the Earth are currently fed as a result of synthetic nitrogen fertilizer use. Fertilizers typically provide, in varying proportions, 6 macronutrients: nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. 8 micronutrients: boron, chlorine, copper, iron, manganese, molybdenum, zinc and nickel. The macronutrients are consumed in larger quantities and are present in plant tissue in quantities from 0.15% to 6.0% on a dry matter basis. Micronutrients are consumed in smaller quantities and are present in plant tissue on the order of parts per million, ranging from 0.15 to 400 ppm dm, or less than 0.04% dm. Only 3 other structural elements are required by all plants: carbon, hydrogen, and oxygen. These nutrients are supplied by water and carbon dioxide in the atmosphere. Labeling of chemical fertilizer. In the US and Canada, the labeling scheme presents 3 numbers separated by dashes. The first number represents the percentage of nitrogen in the product. The second number, phosphorus. And the third, potassium. The generalized form is NPK. A 50-pound bag of fertilizer labeled April 8, 16 contains 8 pounds of nitrogen, 2 pounds of phosphorus, and 4 pounds of potassium. Australian convention adds a 4th number for sulfur. History. Management of soil fertility has been the preoccupation of farmers for thousands of years. The start of the modern science of plant nutrition dates to the 19th century and the work of German chemist Justus von Liebig, among others. John Bennett Laws, an English entrepreneur, began to experiment on the effects of various manures on plants growing in pots in 1837, and a year or two later the experiments were extended to crops in the field. One immediate consequence was that in 1842 he patented a manure formed by treating phosphates with sulfuric acid, and thus was the first to create the artificial manure industry. In the succeeding year he enlisted the services of Joseph Henry Gilbert, with whom he carried on for more than half a century on experiments in raising crops at the Ratarmstead experimental station. The Birkeländer-Euroede process was one of the competing industrial processes in the beginning of nitrogen-based fertilizer production. It was developed by Norwegian industrialist and scientist Christian Birkeland along with his business partner Sam Ude in 1903, based on a method used by Henry Cavendish in 1784. This process was used to fix atmospheric nitrogen into nitric acid, one of several chemical processes generally referred to as nitrogen fixation. The resultant nitric acid was then used as a source of nitrate in the reaction, HNO3H++NO3, which may take place in the presence of water or another proton acceptor. Nitrate is an ion which plants can absorb. A factory based on the process was built in Rjukan and Notodden in Norway, combined with the building of large hydroelectric power facilities. The Birkeland-Ude process is relatively inefficient in terms of energy consumption. Therefore, in the 1910s and 1920s, it was gradually replaced in Norway by a combination of the Haber process and the Ostwald process. The Haber process produces ammonia from methane gas and molecular nitrogen. The ammonia from the Haber process is then converted into nitric acid in the Ostwald process. Forms: fertilizers come in various forms. The most typical form is solid fertilizer in granulated or powdered forms. The next most common form is liquid fertilizer. Some advantages of liquid fertilizer are its immediate effect and wide coverage. There are also slow-release fertilizers which reduce the problem of burning the plants due to excess nitrogen. Polymer coating of fertilizer ingredients gives tablets and spikes a true time release or staged nutrient release of fertilizer nutrients. More recently, organic fertilizer is on the rise as people are resorting to environmental-friendly products. Although organic fertilizers usually contain a lower concentration of nutrients, this lower concentration avoids complication of nitrogen burn harming the plants. In addition, organic fertilizers such as compost and worm castings break down slowly into complex organic structures which build the soil's structure and moisture and nutrient-retaining capabilities. In organic commercial fertilizer, fertilizers are broadly divided into organic fertilizers, or inorganic or commercial fertilizers. Plants can only absorb their required nutrients if they are present in easily dissolved chemical compounds. Both organic and inorganic fertilizers provide the same needed chemical compounds. Organic fertilizers provided other macro and microplant nutrients and are released as the organic matter decays. This may take months or years. Organic fertilizers nearly always have much lower concentrations of plant nutrients and have the usual problems of economical collection, treatment, transportation and distribution. Inorganic fertilizers nearly always are readily dissolved and unless added have few other macro and microplant nutrients nor added any bulk to the soil. Nearly all nitrogen that plants use is in the form of NH3 or NO3 compounds. The usable phosphorus compounds are usually in the form of phosphoric acid and the potassium is typically in the form of potassium chloride. In organic fertilizers, nitrogen, phosphorus and potassium compounds are released from the complex organic compounds as the animal or plant matter decays. In commercial fertilizers, the same required compounds are available in easily dissolved compounds that require no decay. They can be used almost immediately after water is applied. Inorganic fertilizers are usually much more concentrated with up to 64% of their weight being a given plant nutrient, compared to organic fertilizers that only provide 0.4% or less of their weight as a given plant nutrient. Nitrogen fertilizers are often made using the Haber process, which uses natural gas for the hydrogen and nitrogen gas from the air at an elevated temperature and pressure in the presence of a catalyst to form ammonia as the end product. This ammonia is used as a feedstock for other nitrogen fertilizers, such as anhydrous ammonium nitrate and Urea 2. These concentrated products may be diluted with water to form a concentrated liquid fertilizer. Deposits of sodium nitrate are also found. The Atacama Desert in Chile and was one of the original nitrogen-rich inorganic fertilizers used. It is still mined for fertilizer. In the nitrophosphate process or Haber process, phosphate rock with up to a 20% phosphorus content is dissolved with nitric acid to produce a mixture of phosphoric acid and calcium nitrate 2. This can be combined with a potassium fertilizer to produce a compound fertilizer with the three macronutrients N, P and K in easily dissolved form. Phosphate rock can also be processed into water-soluble phosphate with the addition of sulfuric acid to make the phosphoric acid in phosphate fertilizers. Phosphate can also be reduced in an electric furnace to make high-purity phosphorus. However, this is more expensive than the acid process. Potash can be used to make potassium fertilizers. All commercial potash deposits come originally from marine deposits and are often buried deep in the earth. Potash ores are typically rich in potassium chloride and sodium chloride and are obtained by conventional shaft mining with the extracted or ground into a powder. For deep potash deposits, hot water is injected into the potash, which is dissolved and then pumped to the surface where it is concentrated by solar-induced evaporation. Reagents are then added to either the mined or evaporated solutions. The coats the KCl but not NaCl. Air bubbles cling to the N plus KCl and float it to the surface while the NaCl and clay sink to the bottom. The surface is skimmed for the N plus KCl, which is then dried and packaged for use as a K-rich fertilizer. KCl dissolves readily in water and is available quickly for plant nutrition. Compound fertilizers often combine N, P and K fertilizers into easily dissolved pellets. The N, P-K ratios quoted on fertilizers give the weight percent of the fertilizer in nitrogen, phosphate and potash. The use of commercial inorganic fertilizers has increased steadily in the last 50 years, rising almost 20-fold to the current rate of 100 million tons of nitrogen per year. Without commercial fertilizers, it is estimated that about one-third of the food produced now could not be produced. The use of phosphate fertilizers has also increased from 9 million tons per year in 1960 to 40 million tons per year in 2000. A maize crop yielding €6 tons of grain per hectare requires €31.50 a kg of phosphate fertilizer to be applied. Soybean requires €20.25 a kg per hectare. Yara International is the world's largest producer of nitrogen-based fertilizers. Controlled release types, urea and formaldehyde, reacted together to produce sparingly soluble polymers of various molecular weights, is one of the oldest controlled nitrogen release technologies, having been first produced in 1936 and commercialized in 1955. The early product is 60% of the total nitrogen cold water insoluble, and the unreacted less than 15%. Methylene ureas were commercialized in the 1960s and 1970s, having 25 and 60% of the nitrogen cold water insoluble, and unreacted urea nitrogen in the range of 15 to 30%. Isobutylate and diurea, unlike the methylurea polymers, is a single crystalline solid of relatively uniform properties, with about 90% of the nitrogen water insoluble. In the 1960s, the National Fertilizer Development Center began developing sulfur-coated urea. Sulfur was used as the principal coating material because of its low cost and its value as a secondary nutrient. Usually there is another wax or polymer which seals the sulfur. The slow release properties depend on the degradation of the secondary sealant by soil microbes as well as mechanical imperfections in the sulfur. They typically provide 6 to 16 weeks of delayed release in turf applications. When a hard polymer is used as the secondary coating, the properties are a cross between diffusion-controlled particles and traditional sulfur-coated. Other coated products use thermoplastics to produce diffusion-controlled release of urea or soluble inorganic fertilizers. Reactive layer coating can produce thinner, hence cheaper, membrane coatings by applying reactive monomers simultaneously to the soluble particles. Multicoat is a process applying layers of low-cost fatty acid salts with a paraffin topcoat. Besides being more efficient in the utilization of the applied nutrients, slow-release technologies also reduce the impact on the environment and the contamination of the subsurface water. Application: synthetic fertilizers are commonly used for growing all crops, with application rates depending on the soil fertility, usually as measured by a soil test and according to the particular crop. Legumes, for example, fix nitrogen from the atmosphere and generally do not require nitrogen fertilizer. Studies have shown that application of nitrogen fertilizer on off-season cover crops can increase the biomass of these crops, while having a beneficial effect on soil nitrogen levels for the main crop planted during the summer season. Nutrients in soil can be thrown out of balance with high concentrations of fertilizers. The interconnectedness and complexity of this soil food web unregistered trademark means any appraisal of soil function must necessarily take into account interactions with the living communities that exist within the soil. Stability of the system is reduced by the use of nitrogen-containing fertilizers, which cause soil acidification. Applying excessive amounts of fertilizer has negative environmental effects, and wastes the grower's time and money. To avoid over-application, the nutrient status of crops should be assessed. Nutrient deficiency can be detected by visually assessing the physical symptoms of the crop. Nitrogen deficiency, for example, has a distinctive presentation in some species. However, quantitative tests are more reliable for detecting nutrient deficiency before it has significantly affected the crop. Both soil tests and plant tissue tests are used in agriculture to fine-tune nutrient management to the crop's needs. Problems with inorganic fertilizer: see also environmental effects, water pollution, the nutrients, especially nitrates, in fertilizers can cause problems for natural habitats and for human health if they are washed off soil into watercourses or leach through soil into groundwater. In Europe, these problems are being addressed by the European Union's Nitrates Directive. Within Britain, farmers are encouraged to manage their land more sustainably in catchment-sensitive farming. In the US, excess fertilizer runoff is classified as non-point source pollutants due to the inability to quantify the amount entering bodies of water and shallow aquifers. Contamination with impurities, phosphate rocks all contain hazardous elements such as fluorine, heavy metals and radioactive elements. Consequently, common agricultural-grade phosphate fertilizers usually contain impurities such as fluorides, cadmium and uranium, although concentrations of the latter two heavy metals are dependent on the source of the phosphate and the fertilizer production process. These potentially harmful impurities can be removed. However, this significantly increases cost. Highly pure fertilizers are widely available and perhaps best known as the highly water-soluble fertilizers containing blue dyes used around households. These highly water-soluble fertilizers are used in the plant nursery business and are available in larger packages at significantly less cost than retail quantities. There are also some inexpensive retail granular garden fertilizers made with high-purity ingredients. Oregon and Washington, both in the United States, have fertilizer registration programs with online databases listing chemical analyses of fertilizers. The fluoride content of many widely used phosphate fertilizers has increased soil fluoride concentrations, prompting considerable research into the possibility that soil productivity and food quality may be compromised. It has been found that food contamination from fertilizer is of little concern as plants accumulate little fluoride from the soil. Of greater concern is the possibility of fluoride toxicity to livestock that ingest contaminated soils. Also of possible concern are the effects of fluoride on soil microorganisms. Soil acidification, also regular use of acidulated fertilizers generally contribute to the accumulation of soil acidity in soils which progressively increases aluminium availability and hence toxicity. The use of such acidulated fertilizers in the tropical and semi-tropical regions of Indonesia and Malaysia has contributed to soil degradation on a large scale from aluminium toxicity, which can only be countered by applications of limestone or preferably magnesium dolomite, which neutralizes acid soil pH and also provides essential magnesium. Trace mineral depletion. Scientific investigations have indicated a trend of decreasing concentrations of minerals in many foods over the last 50 to 60 years. Intensive farming practices, including the use of inorganic fertilizers, are frequently suggested as reasons for these declines, and organic farming is often suggested as a solution. Although improved crop yields resulting from inorganic NPK fertilizers are known to dilute the concentrations of other nutrients in plants, much of the measured decline can be attributed to the use of progressively higher-yielding crop varieties which produce foods with lower mineral concentrations than their less productive ancestors. It is, therefore, unlikely that organic farming or reduced use of inorganic fertilizers will solve the problem. Foods with high nutrient density are more likely to be achieved using older, lower-yielding varieties or the development of new high-yield, nutrient-dense varieties. Inorganic fertilizers are, in fact, more likely to solve trace mineral deficiency problems than cause them. In Western Australia, deficiencies of zinc, copper, manganese, iron and molybdenum were identified as limiting the growth of broadacre crops in pastures in the 1940s and 1950s. Soils in Western Australia are very old, highly weathered and deficient in many of the major nutrients and trace elements. Since this time, these trace elements are routinely added to inorganic fertilizers used in agriculture in this state. Many other soils around the world are deficient in zinc, leading to deficiency in both plants and humans, and inorganic zinc fertilizers are widely used to solve this problem. Overfertilization. Overfertilization of a vital nutrient can be as detrimental as underfertilization. Fertilizer burn can occur when too much fertilizer is applied, resulting in drying out of the leaves and damage or even death of the plant. Fertilizers vary in their tendency to burn roughly in accordance with their salt index. High energy consumption, In the USA in 2004, 317 billion cubic feet of natural gas were consumed in the industrial production of ammonia, less than 1.5% of total U.S. annual consumption of natural gas. A 2002 report suggested that the production of ammonia consumes about 5% of global natural gas consumption, which is somewhat under 2% of world energy production. Ammonia is overwhelmingly produced from natural gas, but other energy sources, together with a hydrogen source such as water, can be used for the production of nitrogen compounds suitable for fertilizers. The cost of natural gas makes up about 90% of the cost of producing ammonia. The increase in price of natural gases over the past decade, along with other factors such as increasing demand, have contributed to an increase in fertilizer price. Contribution to climate change: the greenhouse gases carbon dioxide, methane and nitrous oxide are produced during the manufacture of nitrogen fertilizer. The effects can be combined into an equivalent amount of carbon dioxide. The amount varies according to the efficiency of the process. The figure for the United Kingdom is over 2 kilograms of carbon dioxide equivalent for each kilogram of ammonium nitrate. Nitrogen fertilizer can be converted by soil bacteria to nitrous oxide, a greenhouse gas. Impacts on mycorrhizas: high levels of fertilizer may cause the breakdown of the symbiotic relationships between plant roots and mycorrhizal fungi. Lack of long-term sustainability: inorganic fertilizers are now produced in ways which theoretically cannot be continued indefinitely by definition, as the resources used in their production are non-renewable. Potassium and phosphorus come from mines and such resources are limited. However, more effective fertilizer utilization practices may decrease present usage from mines. Improved knowledge of crop production practices can potentially decrease fertilizer usage of P and K without reducing the critical need to improve and increase crop yields. Atmospheric nitrogen is effectively unlimited, but this is not in a form useful to plants. To make nitrogen accessible to plants requires nitrogen fixation. Artificial nitrogen fertilizers are typically synthesized using fossil fuels such as natural gas and coal, which are limited resources. In lieu of converting natural gas to syngas for use in the Haber process, it is also possible to convert renewable biomass to syngas to supply the necessary energy for the process, though the amount of land and resources necessary for such a project may be prohibitive. Organic fertilizer. Organic fertilizers include naturally occurring organic materials, or naturally occurring mineral deposits. Poultry litter and cattle manure often create environmental and disposal problems, making their use as fertilizer beneficial. Bones can be processed into phosphate-rich bone meal. However, most are simply buried in landfills. The extent of imbalance in the phosphate and other mineral cycles is such that if all human, animal and plant wastes were recovered to the extent practical and used for fertilizer, mineral fertilizers and synthetic nitrogen would be needed to make up the losses impractical to recover through leaching, atmospheric dispersion and runoff. Benefits of organic fertilizer. Organic fertilizers have been known to improve biodiversity and long-term productivity of soil, and may prove a large depository for excess carbon dioxide. Organic nutrients increase the abundance of soil organisms by providing organic matter and micronutrients for organismal relationships such as fungal mycorrhiza, and can drastically reduce external inputs of pesticides, energy and fertilizer, at the cost of decreased yield. Disadvantages of complex fertilizers. Some composted biowastes used as organic fertilizers may support the growth of pathogens and other disease-causing organisms if not properly composted. Nutrient contents are variable and their release to available forms that the plant can use may not occur at the right plant growth stage. Comparison with inorganic fertilizer. Organic fertilizer nutrient content, solubility, and nutrient release rates are typically all lower than inorganic fertilizers. One study found that over a 140-day period, after 7 leachings, organic fertilizers had released between 25% and 60% of their nitrogen content. Controlled release fertilizers had a relatively constant rate of release. Soluble fertilizer released most of its nitrogen content at the first leaching. In general, the nutrients in organic fertilizer are both more diluted and also much less readily available to plants. Although most organic fertilizers are slow-release fertilizers and cannot cause nitrogen burn or fertilizer burn, some can burn seedlings. Organic fertilizers from composts and other sources can be quite variable from one batch to the next. Without batch testing, amounts of applied nutrient cannot be precisely known. Nevertheless, one or more studies have shown they are at least as effective as chemical fertilizers over longer periods of use. Examples of organic fertilizer: chicken litter, which consists of chicken manure mixed with sawdust, is an organic fertilizer that has been shown to better condition soil for harvest than synthesized fertilizer. Researchers at the Agricultural Research Service studied the effects of using chicken litter, an organic fertilizer, versus synthetic fertilizers on cotton fields, and found that fields fertilized with chicken litter had a 12% increase in cotton yields over fields fertilized with synthetic fertilizer. In addition to higher yields, researchers valued commercially sold chicken litter at a $17 per ton premium over the traditional valuations of $61 per ton due to value added as a soil conditioner. Other ARS studies have found that algae used to capture nitrogen and phosphorus runoff from agricultural fields can not only prevent water contamination of these nutrients, but also can be used as an organic fertilizer. ARS scientists originally developed the algal turf scrubber to reduce nutrient runoff and increase quality of water flowing into streams, rivers, and lakes. They found that this nutrient-rich algae, once dried, can be applied to cucumber and corn seedlings and result in growth comparable to that seen using synthetic fertilizers. Examples: compost, rock phosphate, bone meal, manure, alfalfa, wood chip sawdust, raw langbionite, cover crops, unprocessed natural potassium sulfate, rock powder, ash, blood meal, fish emulsion, organic fertilizer sources, Animal-sourced and human urea are suitable for application organic agriculture, while pure synthetic forms of urea are not. The common thread that can be seen through these examples is that organic agriculture attempts to define itself through minimal processing, as well as being naturally occurring or via natural biological processes such as composting. Besides immediate application of urea to the soil, urine can also be improved by converting it to storvite, already done with human urine by a Dutch firm. The conversion is performed by adding magnesium to the urine. An added economical advantage of using urine as fertilizer is that it contains a large amount of phosphorus. Recycled sewage sludge as soil amendment is only available to less than 1% of U.S. agricultural land. Industrial pollutants in sewage sludge prevents recycling it as fertilizer. The USDA prohibits use of sewage sludge in organic agricultural operations in the U.S. due to industrial pollution, pharmaceuticals, hormones, heavy metals, and other factors. The USDA now requires third-party certification of high-nitrogen liquid organic fertilizers sold in the U.S. Plant, leguminous cover crops or fertilizer trees are also grown to enrich soil as a green manure through nitrogen fixation from the atmosphere, as well as phosphorus content of soils. Mineral, mine-powdered limestone, rock phosphate and sodium nitrate, are inorganic compounds which are energetically intensive to harvest and are approved for usage in organic agriculture in minimal amounts. Environmental effects. Eutrophication. The nitrogen-rich compounds found in fertilizer runoff are the primary cause of serious oxygen depletion in many parts of the ocean, especially in coastal zones. The resulting lack of dissolved oxygen is greatly reducing the ability of these areas to sustain oceanic fauna. Visually, water may become cloudy and discolored. About half of all the lakes in the United States are now eutrophic, while the number of oceanic dead zones near inhabited coastlines are increasing. As of 2006, the application of nitrogen fertilizer is being increasingly controlled in northwestern Europe and the United States. If eutrophication can be reversed, it may take decades before the accumulated nitrates in groundwater can be broken down by natural processes. Blue baby syndrome, high application rates of inorganic nitrogen fertilizers in order to maximize crop yields, combined with the high solubilities of these fertilizers, leads to increased runoff into surface water as well as leaching into groundwater. The use of ammonium nitrate in inorganic fertilizers is particularly damaging, as plants absorb ammonium ions preferentially over nitrate ions, while excess nitrate ions which are not absorbed dissolve into runoff or groundwater. Nitrate levels above 10 mg per liter in groundwater can cause blue baby syndrome, leading to hypoxia. Soil acidification. Nitrogen-containing inorganic and organic fertilizers can cause soil acidification when added. This may lead to decreases in nutrient availability which may be offset by liming. Persistent organic pollutants. Toxic persistent organic pollutants, such as dioxins, polychlorinated dibenzo-P-dioxins, and polychlorinated dibenzofurans have been detected in agricultural fertilizers and soil amendments. Heavy metal accumulation. The concentration of cadmium in phosphorus-containing fertilizers varies considerably. For example, monoammonium phosphate fertilizer may have a cadmium content of as low as 0.14 mg per kilogram or as high as 50.9 mg per kilogram. This is because the phosphate rock used in their manufacture can contain as much as 188 mg per kilogram cadmium. Continuous use of high cadmium fertilizer can contaminate soil and plants. A proposal to limit the cadmium content of phosphate fertilizers is being considered by the European Commission. Steel industry wastes, recycled into fertilizers for their high levels of zinc. Wastes can include the following toxic metals: lead, arsenic, cadmium, chromium, and nickel. The most common toxic elements in this type of fertilizer are mercury, lead, and arsenic. Radioactive element accumulation. Phosphate rocks and fertilizers derived from them contain radioactive elements of the uranium-238 series and thorium-232 series. Concentrations of these radionuclides in the fertilizers vary considerably, and depend both on their concentrations in the parent phosphate rock, and on the fertilizer production process. Uranium-238 concentrations can range from 7 to 100 pCig in phosphate rock and from 1 to 67 pCig in phosphate fertilizers. Where high annual rates of phosphorus fertilizer are used, this can result in uranium-238 concentrations in soils and drainage waters that are several times greater than are normally present. However, the impact of these increases on the risk to human health from radionuclide contamination of foods is very small. Also, highly radioactive polonium-210 contained in phosphate fertilizers is absorbed by the roots of plants and stored in its tissues. Tobacco derived from plants fertilized by rock phosphates contains polonium-210 which emits alpha radiation estimated to cause about 11,700 lung cancer deaths each year worldwide. For these reasons, it is recommended that nutrient budgeting, through careful observation and monitoring of crops, take place to mitigate the effects of excess fertilizer application. Atmosphere. Methane emissions from crop fields are increased by the application of ammonium-based fertilizers. These emissions contribute greatly to global climate change as methane is a potent greenhouse gas. Through the increasing use of nitrogen fertilizer, which was used at a rate of about 110 million tons per year in 2012 to the already existing amount of reactive nitrogen, nitrous oxide has become the third most important greenhouse gas after carbon dioxide and methane. It has a global warming potential 296 times larger than an equal mass of carbon dioxide, and it also contributes to stratospheric ozone depletion. The use of fertilizers on a global scale emits significant quantities of greenhouse gas into the atmosphere. Emissions come about through the use of animal manures and urea, which release methane, nitrous oxide, ammonia, and carbon dioxide in varying quantities depending on their form and management. Fertilizers that use nitric acid or ammonium bicarbonate, the production and application of which results in emissions of nitrogen oxides, nitrous oxide, ammonia and carbon dioxide into the atmosphere. By changing processes and procedures, it is possible to mitigate some, but not all, of these effects on anthropogenic climate change. Other problems: increased pest fitness. Excessive nitrogen fertilizer applications can also lead to pest problems by increasing the birth rate, longevity and overall fitness of certain agricultural pests, such as aphids. See also, Fertigation, History of Organic Farming, Milorganite, Phosphogypsum, Soil Defertilization, History of Fertilizer, References. External links, Nitrogen for Feeding Our Food, Its Earthly Origin, Haber Process, The Fertilizer Institute, U.S. Fertilizer Industry Association, International Fertilizer Industry Association, European Fertilizer Manufacturers Association, How to Read Fertilizer Tags article, Agriculture Guide, Complete Guide to Fertilizers and Fertilization, 4R's Nutrient Stewardship Program from the Fertilizer Institute.